Ian Muirhead is going to present, but we're going to start with his first slide, which has a video on it. So if we have that video.
Good morning, ladies and gentlemen. My name's Ian Muirhead, and I'm here from Annakale in Scotland. I started out with that video because that's basically where we started our journey as a company. It was literally a serendipitous find by the researchers to develop a plasma loudspeaker. And what you saw there was the recording of that loudspeaker and the first device that was made. That device has turned into this plasma head, which I'm going on to tell you about in our journey going forward from here. So normally when you go to business school, you go find a big market, find a problem to solve, and drive everything from there. But sometimes life doesn't work out like that. We actually had, as I say, an accidental find. Now, the problem was when you switched on this plasma loudspeaker, it gave out a lot of ozone. And there are two key things the researchers did. Was one, switch it off before they poisoned themselves. And second was to realize that this thing generated a lot of ozone quickly and easily. And the challenge was then how to harness that. And they realized that the front electrode was very smooth, and rather than generating ozone in the air, by attaching a plastic bag to it, they could actually create ozone inside a plastic bag. And you may ask yourselves, so what? And what I'd like to go on now and tell you about is why, the so what. So ozone has been around for a long time. It's been known about since the 19th century, but it's a very difficult gas to handle. It's difficult to generate, very difficult to store, and in fact it can be explosive when stored. But it's a very, very good germicide. It's actually much better than chlorine. And what we're doing is basically taking the oxygen, it's inside a sealed container, and using our plasma electrode from the outside, breaking down the oxygen into its individual state, and then that recombines to ozone, and that causes a germicidal effect inside the plastic bag. And I have to emphasize here, we're not adding any chemicals at all to the package. We're not breaking the seal of the package. All we're doing is breaking down the oxygen of the air inside that container and turning it into ozone. So it's, from a sustainability point of view, we're not introducing gases, and that has obviously consequential effects. So it's sustainable and repeatable and much easier to handle than any other form of ozone. So this is a demonstration of it in real life. So the technology you saw from the loudspeaker has now moved a further 2 generations on. So this is a typical food pack tray that you would get your fish or whatever in. The plasma head is now coming down onto the top of the plastic, and you'll see a little glow on top. And that's where we're generating the plasma in a very thin layer just underneath the polythene lid. So that container will now contain ozone. And it will go off and actually basically suck the ozone out to just show you how much ozone is in there. So again, emphasize, we have not broken the seal. We have not added any chemicals. All we have done is take the oxygen, break it down, it recombines back to ozone. Ozone has a short life, and at room temperature, that will decay back to oxygen again inside an hour. So, but the key thing in that time, what it has done is knock back the molds, yeast, bacteria, and viruses on the surfaces of anything that's contained inside it. So that, for us, could be a food product, it could be a medical device, or anything else you want, including electronics. And that's one of the key things about this. The way we generate our plasma is independent of what's inside the pack. So the first markets we're looking to address, and already addressing, are the food packaging industry and the medical device industry. So food, we're already working on a range of food products, including fruits and vegetables, and fish and bakery, and I'll go on and talk about these. And in medical, its ability to actually sterilize a device in the package, but not only that, to then go on and store it in a sterile package. So it has many, multiple applications. So looking at the food. Coming at it from the UK perspective, food waste is a major issue, and it's a global major issue now. Currently, there are about 50 million tons of waste in the food supply chain, and that represents about £5 billion of value. In the EU, 90 million tons, and I'll go on to talk about the US in a second. How that's addressed at the moment for food shelf life is the use of additives and something called modified atmospheric packaging. And there you're introducing a gas to the product, into the container. And that is a £10 billion market. So these are the segments we are going after. In the US, it's the same as Europe in terms of where the food loss is through the supply chain, right from the gate to your plate. And one of the key things I was going to highlight here, if you just take a look at the seafood and fruit and vegetables, we're looking at around the 50% of the food in the supply chain goes to waste. Something needs to be done about that on a long-term basis. And one of the things you can do is actually extend the shelf life of food so it doesn't go off as quickly and gets used in the supply chain before it actually goes to then landfill. Now what we are addressing is knocking back molds, yeast, and bacteria. We can't do things about it going dry or going soggy. So things like sandwiches go soggy before they go off. So you need to be, we are addressing the issue of yeast molds, etc. So I touched on modified atmospheric packaging, and as I say, that's where you're introducing gas to the mixture to basically sustain, knock back or hold the bacterial growth in place, and that's a huge industry dominated by some large gas suppliers. Food additives, again, another large area, and also they're developing fresh packaging technologies. We can work alongside these, and in some instances, we can actually replace them. And it's all about how many extra days you can get into the shelf life, and on top of that, actually killing some of the nasty bacteria, which actually might lead to safety issues as well. So it's shelf life and safety. So an example here, where we take control packages of standard retail-type tomatoes, and typically it's a 5-day shelf life. With our ozone treatment, we can get that up to 20 days of completely mold-free tomatoes. In bakery, we've demonstrated again on the left-hand side, you have the controls, which are untreated. On the right-hand side, you have the treated ones. And again, we can go much greater number of days in the supply chain without the product actually going off. So again, to answer the so what question, well, as I say, it improves food quality. In terms of when you go to the retail shelf, you often find where it's blueberries or whatever, you'll have some moldy samples in what you buy. We can reduce the number of moldy product within the existing retail shelf timeline. But we can also extend that timeline. So that's important for the food producers and the food retailers. In speaking to the bakery companies, they're very interested in removing additives, so getting clean label product. So they don't want to extend the shelf life, but have the same shelf life without all the additives added. And that's what we're working on with them. We can improve the amount of product that is actually going to landfill. So clearly that saves money and gas emissions. And right through the supply chain, if you're reducing the amount of food you're having to take through the supply chain, it has knock-on effects in CO2, transport, and then right down into the amount of fertilizer you use, the water and irrigation. So it really does have knock-on effects right the way through the supply chain. So where are we at in the process? We're already engaged with a number of UK customers, and we've shipped our first equipment to a a large chilled food good company, and about to ship to a fish manufacturer and a bakery. Typical process for us is to do some look-see trials, take the unit on site, and then for them to integrate it into their processes. We'll be working on a model and a lease of the equipment and a cost per pack, and that cost per pack will be way lower than the current modified atmosphere packaging costs. So we believe we've got a very sustainable business model going forward and bringing benefit to our customers and partners. That's me touched on the food. I'd like to go on now and talk a little bit more about the medical side of things. As I say, ozone is a recognized sterilization process, but pretty much the market is dominated by things like ETO, gamma, and steam sterilization. But a lot of the challenges of products which actually don't accept any of those processes. Products are getting more complex. They may have electronics in them, batteries, complex materials. They may actually have biologics in them as well. So there's a very large opportunity which has been unsatisfied at the moment with the current products which are actually shipped onto the market. And that's the part we're looking to address. So what do we bring to the medical device sterilization? As I say, it's a very powerful germicide, and it's well recognized as such. But what we're developing is a small footprint box, which actually means you can actually sterilize in the clinic. So a lot of times, such as flexible endoscopes, they go back to a centralized cleaning process. That takes time, goes back to the patient. So they actually have multiple devices which are not in use all the time. We have the capability, after being washed or wiped down, to actually sterilize at the point of use, so before the next patient comes on board. Also, there's some products which are just getting wiped down without actually being high-level decontaminated or sterilized before they go to the next patient. And increasingly, we're seeing warnings coming out from the health service industry saying, look, we need to deal with this. You're passing infection from patient to patient. Operator safety is also an issue. So a lot of the hydrogen peroxide systems, etc., are not easy to use from an operator safety point of view. What we have is a strong germicide, but because it's generated and contained inside a container, it's very easy for the operator to use in a very safe manner. And one of the important things is, after it's been sterilized, it's maintained in a sterile storage container. A lot of the current endoscopes, after being cleaned, are dried and put into a drying cabinet. The problem is when you open that cabinet to take one of them out, you've exposed all the other ones to potential contamination. So by packing them individually, which a lot of them already are, we can actually store it in a sterile environment. So we're at the process now of, by the time I go back to the UK, we'll have our first prototype, and we'll be evaluating across a wide range of infections. What I'm going to show here is a little bit of the science behind it. These are water droplets on agar plate, so it's a medium which has been doped, or the water droplets have been doped with salmonella. And what you're about to see is those treated with ozone. And what you're seeing here is the green blobs are glowing salmonella bugs. So these have been basically doctored to make them glow while they're still alive. So if I start the play button, you'll shortly see a little ozone zap, and the green bugs are still all very happy and chunting around. You'll see a second big zap in a second, which is where we introduced our ozone. You'll start to see the green glow move towards the center and decay. That is the salmonella bugs dying in real time with our ozone technology. So we have first-hand scientific experience of how we're actually killing those products. And again, that's ozone moving into the water droplet. So this is very good for us in terms of building up our data for both the food and medical instrumentation side of the business. So as I say, we've gone on. We have done a lot of work in testing endoscopes and taking the lumens, the very narrow pipes that go through a flexible endoscope, testing them against a wide range of fairly nasty bugs. And we've demonstrated log 9 kill. So anything greater than the log 6 kill is a high level of decontamination. Log 9, 10, 11 kill, you're getting to endpoint sterilization. So in food, we're decontaminating. In some medical devices, it's high level decontamination, and at some point, it's endpoint sterilization. And we can change our ozone process to fit those different categories. So what does that mean from a value proposition for the medical industry? As I say, it touches on the ability to have ozone sterilizer at the point of use, operator safety, time and money benefits, and we can actually introduce high-level sterilization to an application which has at the moment just been wiped down and cleaned. So the quality of healthcare by transfer of infection is improved. One of the big potential upsides that is in there is about 18 months ago, a US group came out with papers suggesting that gaseous ozone can actually denature prions. So now we're looking to work with some of the leading prion research teams, because this actually could then contribute towards the issues of CGD, etc. Now, this plasma head is of this size. The medical device one will be much smaller, and we're actually designing it to run off a 12-volt battery, which can be recharged off a small solar cell. So there we're looking to actually bring a low-cost sterilization device to developing economies. So, for instance, if you have a remote area with a dentist going around villages, often the actual dental instruments are not cleaned between patient to patient. They may be washed, not necessarily the cleanest of water. Here, you could actually put them in a plastic bag, using our plasma on a little portable system, actually sterilize them between patients. So we believe this has strong humanitarian benefits, as well as benefits to the large global food supply chain. So where we're at, as I say, with the medical device one, we have our first unit about to be delivered, and we'll be evaluating that in the next few weeks going forward. So on the carpet side of it, one of the areas beyond what we're currently doing is drain contamination. We've actually had the food customers we've been speaking to and also the health service come to us and say, can you attack biofilms in drain wells? So we've now submitted a patent, and we're actually developing a prototype to look at decontaminating drain wells using our ozone plasma technology. The team behind it, I want to really acknowledge Hugh Potts and Declan Diver, who are the key academic founders who are behind the technology. And at the moment, we're building up our advisory team from people from the sterilization industry and people from the food industry, and we're building our board out going forward. So in summary, what we have is a distributed sterilization technology, the ability to actually create ozone easily, low cost, and safely, and it has a wide number of applications. And finally, I was asked, what would we do if we were to win the prize? Well, we are a micro SME. The team you saw there, that is us, basically. We are really at that early stage. We've had seed funding. When I go back to the UK, I go straight down to London, to the city, to start raising venture capital money for our next stage of growth. If we were to be successful, I would do that with a spring in my step. Thank you very much.
That's great. Questions?
Yes, so I work in the public aquarium industry, and we use ozone extensively for water disinfection.
Yeah.
And it achieves its germicidal effect through this potent oxidation, and we have to move the ozone around in exotic materials like kynar and so on. I'm wondering about the effects of your in situ ozone generation on the packaging itself and also on the food, because oxidation of food is obviously not necessarily a desirable thing.
Yeah. As you're probably well aware, there's a whole industry of ozonated water. What we're talking about here is gaseous ozone, so there's two quite different animals in that respect. From a materials point of view, when I look at the medical devices, it's compatible with a wide range of materials that's already used in the medical device industry. And a lot of those that are not compatible, say, with gamma or ETO sterilization. So there are certain segments of the market which potentially ozone is the only potential solution for it. There are some materials ozone would attack, so you have to be careful and not use those. With the food, it's an iterative process to find the right level of ozone to use by food type. So if you don't have enough ozone there, you don't knock the mold and yeast back sufficiently. If you do hit it with too much ozone, you do get an oxidation effect and have a taste dent. So there's a window you have to develop going forward. So we're building up a library at the moment of the different types of ozone that you need for it. On the packaging side, we've done a lot of work on migration testing of impact of the ozone plasma, and we've found no impact at all in terms of migration of material or anything from the mist films that's in there onto the food. And so that's a key thing from a regulatory point of view that makes sure. Where actually ozone generation is a very, very short period of time. And so the impact on the film is minimal. You do get some physical mark on it, but again, within a couple of days, you don't see that mark at all.
Questions?
you're talking about extending food packaging life. Can you talk about two things? One is how many more days or percentage are you potentially getting? And then when you're dealing with blueberries or tomatoes, which are typically shipped so they're open to the air, or if they're packaged, they're open air packages. When do you apply that? Is it at the end of the shipping, or is it the beginning of shipping, you treat it and then put it down later?
So in terms of the packaging, if I take the tomatoes as an example, the dose you give to tomatoes will be different from what you give to bakery. So it's a different amount of ozone you would do that. What we're looking to do is actually introduce this immediately after basically the food has been put into the food tray and heat sealed. So it's part of the process in line straight after the food has been packaged. In terms of shelf life, some products is 1 or 2 days, some is 10 days. So it's again varies from product to product. So the second part of your question was the...
So for things that are shipped open air?
Yeah, thank you. So again, that's quite different from region to region. If I take tomatoes, in the US, I believe they're much more open packaging. In Europe, it's actually much more small sealed packages, and a lot of it's now snacking tomatoes. So there are little packs with small tomatoes in them. We're actually working with packaging companies who have got, looking at larger tray packs, who have a layer on top of it, and we can either be paper or film packaging is breathable. We can actually use micro-perforated film. So these, one of the challenges with vegetables that there is fire, but using micro-perforated, you can control the respiration, but we can also treat with the ozone. So it's a combination of getting the packaging right and the ozone right. And a lot of the large suppliers are working with us to actually optimize the package for the ozone treatment to give the benefit through the supply chain. Also, we've been asked about logistics. Can we actually do something on the pallet hoods in the large cases? And again, we're working on that as well. So through the supply chain is different applications of the same technology, but in a different way.
Cool. We have a question over here.
I think you just answered part of it a minute ago, because my question was in relation to the packaging itself, especially when so much of the food waste comes from the fresh fruits and vegetables that is sold without packaging, and many eco-conscious buyers will prefer to buy produce not in packages to reduce the waste of the packaging. So I was wondering if you're looking at ways in which to address how that might be handled in shipment without needing the packaging. And then the same question would also apply in the medical setting. A lot of your medical devices are packaged. Is there a way to use this technology without such heavy reliance on packaging individually?
Yeah. Well, if I take the example of a lot of the modified atmospheric packaging, it's special packaging and special film to deal with that. So if you can actually use an ozone rather than a MAP process, you can take some of the cost out of the package. We can just work with a more standard package, standard film and air. So our process is lower cost, with the same impact as MAP on some of the products. When I'm speaking to US suppliers on the tray carrying, yes, those are then shipped out, but there's a lot of waste in the process. So looking at the film they put on top of it, a breathable film, treatment at the point, at the wholesalers, or even actually at the farm potentially. So the time it actually reaches the retailer, there are a lot less wastage in the product by the time it gets there. And there are cultural differences in terms of, as I say, how food is packaged from region to region. We've got very, very good results with table grapes. So one of the things we're looking at with table grapes, can we actually go back to the key region suppliers for table grapes at the packaging house and introduce it here? And so actually stop the waste right at the point before it even ships off the vineyard.
And Ian, one more over here.
One more, meaning two quick ones?
No, I'm sorry, I just meant another one. We've got about 4 minutes.
Oh, okay. So two questions. One of them is, we've been underestimating bacteria for thousands of years. They're very adaptable. So can second and third generation and generations of bacteria adapt to your product in some set of ways?
I'm not a microbiologist, I have to hold my hand physicist around a microbiologist, but my understanding is that they will not adapt to the ozone. And we're seeing that with the biofilms in terms of, it's very difficult to get rid of biofilms because sometimes there's a protective layer of bacteria beneath the other ones, so you might get rid of the top ones and not get rid of the bottom ones. In the work we've been doing, we're actually getting right back to the base on the biofilms if you put in enough ozone in there. And the good thing with some of the medical applications, you can give it a lot of ozone. You don't need to worry about tasting in any shape or form, so you can hit it with a lot of ozone. We've also been approached by tissue banks. Tissue banks for going into experiments. They actually, to improve the quality of the tissue that's going into further experiments, they want to make sure it's totally free of virus, bacteria, etc. going forward. So they actually want to make sure it's clean, so don't ruin the rest of the experiment process.
Yeah, go ahead.
Go ahead. Okay, so the second question is, bacteria doesn't leave the universe, it goes somewhere. When you kill the bacteria, where do they go?
Bacteria basically just die. I mean, it's literally, and there's no
residue. No
when they just disintegrate into, it's like burning them off effectively.
Okay, and
I'm not a microbiologist, so I'll probably get using the wrong terminology there.
Well, neither am I. So the last question is, when I got on the airplanes, 2 of them to come here, there were people wiping down the seats and wiping down their tray tables and things like that with a little square something or others. Does your product have application in those?
Another discovery in the lab.
Sure, it's bacterial. So,
we can clean surfaces, and we have actually done some work in cleaning specialist optics to actually remove any traces before bonding. The challenge there is you need a sealed environment. So effectively we have our ozone plasma head that you would then need a sort of little skirt around it so that it doesn't actually ozone escape. But yes, we can clean surfaces. And I know people are looking at ozone for cleaning food processing instruments, so knives, etc. Surgical knives is another area as well. So, but the real benefit is when you can actually keep this inside a sealed container.
Okay. Thanks, Joan. A question from Mary.
Hi, great presentation.
Thank you.
Just one question, please. As you say, it's a very small team. I'd like to know a tiny bit more detail about your patent, and would you want to license, because you've got limitations, obviously, as a small team, and
Yes.
you're trying to get this covered globally.
So the original patent was filed by Glasgow University, and that's been assigned to Annika, so the spin-out company, and the university have an equity stake in that. So the core patent is going through its filings. It's the final state. In fact, I expect it to get granted in the US in the next couple of months, and it's going worldwide through the different stages of the PCT. Since then, we've actually, as a company, filed a further 4 patents since we put ourselves in place. And part of our challenge is there are too many things you can do with this. And as evident with an early stage company, you have to focus, start getting the early things right, and then come back to the other things. So there'll be some areas where we would look to license. I mean, if I take the surface cleaning one, that would be a good example where we would not expect to take, or we would not propose to take a surface cleaning product to market, but we could potentially license the technology. As we build up our OEM partnerships, clearly food and medical are quite different business models, they're different sort of industries. So we'll be building up a team dedicated to food, dedicated to medical, and actually may split them off as separate companies at some stage, or do a global license in one of the areas.
Good. Ian, thank you very much.
Thank you.
Great job.
And now, time for the preservative enchantment. The nerve to serve hors d'oeuvres infers that serves preserve great Merlin's balls.
I bet there's an easier way.
No, it's an ancient ritual. The nerve to serve hors d'oeuvres infers that serfs prefer their herbs. No!
Really? Well, I just read in the science tome that...
Science! Nothing but codswallop. How can that work?
uses a machine.
You mean a cauldron?
And electricity.
You mean the ears of a snake?
And plasma.
You mean the tail of a newt?
And ozone!
Ozone? You mean...
No, it's a myth.
It's all a myth. Scientism is ridiculous, and so are you! The nerve to serve hors d'oeuvres infers that... The nerve to serve hors d'oeuvres infers that serfs prefer their herbs preserved and not reserved. A serf whose turf is tough as earth is worth his girth and dirt and mirth and... Ah!
Nonsense.